Alright, so let's try to finish up the basic material 1.3 with the Squeeze Theorem, and then they give us the Squeeze Theorem mostly because then they use it for the limit as x goes to 0 of sine x over x, and the limit as x goes to 0 of 1 minus cosine x all over x. So the Squeeze Theorem, what you need to get is that the two limits involved on either side need to be the same. So the way they talk about the Squeeze Theorem is they say, okay, we have these three functions, and whoops, I need f here, not g. F of x is less than or equal to g of x. So you have this for all x. Okay, or at least all x that we care about. So you could actually say for all x in an open interval containing C. Oops, containing C. Okay, except maybe, like comma, except maybe C. In other words, it doesn't, because of the limit, it's all about getting close. We don't really care what's happening right at C. So we have this. Then, what we need for this Squeeze Theorem to work is that we need the limit as x goes to C of h of x to be equal to the limit as x goes to C of g of x. Okay, and then that's equal to some L. But this is very important that those two limits be equal. It's not just that the limit of h as x goes to C exists and the limit of g as x goes to C exists. They have to exist and be equal, because that's how we get the squeeze part. So, then the limit as x goes to C of f of x is also equal to L. In the picture, it just is that, okay, if we have C here somewhere, and we know that h is always bigger than f, so we'll just wait. H is always smaller, so g is always bigger. So here's g of x, and then h of x. We'll kind of draw it, say like this. H of x. Well, then, it really just doesn't matter what f does, right? I can have f doing all sorts of, well, that's not a function if I'm not careful there, but, right, it has to, even if it's kind of wiggly and so forth, it has to make it in here. So here's f of x. It has no other option but to go to this value here, L. Okay, because if it's bigger than h but less than g, then, and they both meet up here, then that's all it can do. But see, that's the important part. They have to meet up. If they didn't meet up, right, if we had a situation like this, where, okay, we've got that one there and that one there, then, here's g of x, here's h of x. Well, f doesn't have to have a limit. It could do all sorts of different behaviors, but at the very least, right, it could come in here like this. There's f of x, and it could go this way, and one of these two would be an open circle for f of x, but then that limit at c doesn't exist. So see, it's very important that those two functions equal each other. So that's the squeeze theorem. Is just saying that. And then I'll go to a new page here. So these other two limits that turn out to be very nice and very important is, that the limit as x goes to 0 if sine of x over x is equal to 1, and the limit as x goes to 0 of 1 minus cosine of x over x is equal to 0. Now, if we look at those graphically, so you could plot this on Desmos, or you could plot the two functions separately. So if you plot these two functions separately, let's come down here a little bit. Right, I know sine of x is doing something like that, and y equals x is doing that. So here's y equals x, here's y equals sine of x. Then you see, as they come in, they look very much alike. Y equals x and y equals sine x. And so, if you zoom in, they look very, very much alike. And so these values are about the same, and so that's why when you take the ratio, you get 1, because the values are about the same. And if we try to look at something like, well, what does cosine of x look like, right? Cosine of x does something like this at 0, where that's 1. So if I take 1 minus that, so this is cosine of x, kind of try to figure out what happens. So if I take 1 minus this, I get positive numbers, but it's at 0, right? Because 1 minus that is 0. And by the time I get here, it's 1, and it'll be sort of that opposite shape. And so you get something like this. And again, if I, so here's 1 minus cosine of x. And then if I take that y equal x, well, notice, the difference here, this is getting really close to 0, it's getting really small, but this is just kind of coming down. It's also getting close to 0, but look how much smaller this one looks just kind of in the picture. And so it seems reasonable that maybe, in the end, this would be much, much smaller than that. And so that limit would be 0. Seems okay, sort of reasonable. And again, I could just plot this and look at what that function looks like on something like Desmos, and I should see that it looks like it passes through 0, 0. Now, so those are those two limits, and it's kind of interesting then that if you there are a couple of examples they give. Okay, so this is example 9. They mention that the limit as x goes to 0, they want to look at tangent x over x. Well, so here the idea is, well, I need a trig identity. So here's limit x goes to 0. So tangent is sine over cosine, so I get sine of x over cosine of x, well, times x, like that. And then, again, we use that multiplicative property. So I have the limit as x goes to 0 of sine of x over x, and then the limit as x goes to 0 of 1 over cosine of x. And once again, though, we know that that limit is 1, and here we can do direct substitution. So we get 1 from that one, and by doing direct substitution I get 1 over cosine of 0, but cosine of 0 is 1. I get 1 times 1, and that's 1. And their example 10, we have to do a little bit of algebraic trickery here. So limit as x goes to 0 of sine of 4x over x. Well, so here's the problem. I know that sine of x over x goes to 1, but I don't know what sine of 4x over x does. However, if I multiply by 4 over 4, and so if I take this limit as x goes to 0 and by 4 over 4, well, I know that's just a 1, so I'm just multiplying by 1 times the limit of sine 4x over x as x goes to 0. Then, now I'm going to put these different pieces together. I'm going to move this 4 in here, and I can do that. And this I'm just going to leave as the limit as x goes to 0 of 4, but I know that's 4. And so then I have the limit as x goes to 0 of sine of 4x over 4x. And you see there's 4x, there's 4x. And so now I have 4, but if I let y equal 4x, now the key here is that as x goes to 0, right, as this goes to 0, so will y. That will also go to 0. That's important that we keep track of that. So y is going to 0, and I make that substitution. This is sine of y over y, but now I know that that is 1, and I get 4 times 1, or 4. So we end up with 4 there. Now, and back here, I realize that I guess I didn't actually have to put this limit on here. I could have just said 4 over 4, that's 1, times the limit as x goes to 0 of sine of 4x over x. And then moved that 4 inside, and that would be fine. I didn't actually need to put that limit sign on there. But those are, using these trig identities to look at limits. And trig identities, here's an algebraic identity. But a couple of examples that use these particular limits. So here, we're just supposed to kind of remember that the limit of sine x over x is 1, and the limit with that, so we want to just remember about these two limits, that here we get 1 and here we get 0. Maybe, there we go, 0. And I think that does it for the main material of section 1.3. So we'll call that one done.